All right, cool. So we are going to move on, and I want to introduce you guys to a few of the different variables and values we're going to be dealing with when it comes to electricity. We're going to be looking at voltage, current, and resistance, all of which you hopefully looked at in grade 9, but I want to go over them again to make sure we have a good understanding of what those all mean. And to try and paint the picture of what is happening with regards to voltage, current, and resistance, I am going to show you my water slide analogy. So this is my water slide, and you cannot make fun of my drawings. That is not allowed. So if you can just picture here, what I have here is a ladder. And so let's say you guys are the people wanting to go up the water slide, and I have all of you guys going up the water slide. All your different hair and different people, and one of you guys can have a hat. Okay, so what you have here is you have all of these little people going up the water or up the ladder to get to the top of the water slide. And then you, once you get to the top, all these little people, you guys would go down and go into the water. And because you guys are at a water park and it's super fun, you would go through the cycle all over again. You would get out of the pool, you would go up, and you'd come down. So this is representing a circuit. All right. And what I'm going to look at is how voltage, current, and resistance have to do with this circuit. So let's take a look at the definitions of voltage, current, and resistance. So voltage is the electric potential difference that's often created by a battery or an electric cell or some sort of power source. So we are looking at a electric potential difference. So the last time you guys looked at differences of potential energy, you may have remembered that we were looking at gravitational potential energy in the energy unit. So what you can actually notice here is there is a difference in potential energy between the bottom of this ladder and the top of the ladder. So what I'm trying to explain here is that this ladder would kind of be your power source. So this is your power source that would show you your voltage, your difference in electric potential energy that is created in this circuit. So the larger this ladder, the more electric potential difference is created. So the higher the ladder, the higher the voltage of this circuit. The shorter the ladder, the shorter the electric potential of this circuit. All right, and so that would change the voltage. The shorter the ladder, the smaller the voltage. The higher the ladder, the higher the voltage. Okay. Now, let's take a look at current. Current in a circuit refers to the amount of charge that is flowing through a conductor, so that's usually your electric wire. So the amount of charge that's flowing through that wire per second. And we measure this in amperes. So back to my water slide analogy, all of these different little people, those are my charges. Those are my charges flowing through my circuit. They're gaining potential, electric potential, and then they're flowing through. If I were to increase the amount of people going up my water slide, I would be increasing the current. So the more charge going through a circuit, the more current. The less charge, the less current. Okay? Now, going on to my last variable that we're going to be looking at in this unit, I'm looking at resistance. So resistance is how difficult is it for a current to flow. So that is all measured by the slide. So our resistance in a circuit is typically dependent on the type of material that the conductor might be made out of, the temperature of the conductor. But the resistance is definitely also based on the type of the slide. So you might have different resistors that have higher resistance or lower resistance. And that's what we are going to be looking at in this unit. So I can actually provide a bunch of examples. Let's see how all of this plays into a circuit. So what I am going to show you guys is an actual circuit. So we have our voltage, our current, and our resistance. So I am going to draw a circuit. And I am going to draw a circuit that has a resistor in it. Okay? So what I am going to do is here I have a case in which I have a power source. This is my power source, and that creates a voltage. And so my voltage is represented by this ladder. And then I have a resistor. So that resistor is here. All right. So if I have a voltage here of 12 volts along this battery, so that means all of my current is gaining 12 volts. So they're gaining an electric potential of 12 volts. When they are flowing through this wire, they then hit a resistor, and that resistor is represented by this slide. Okay? So what's going on here is that I have a current flowing through this slide, and to actually get back here, they have to go down 12 volts. So if all of my current gained 12 volts as they came up this ladder, they would then have to drop 12 volts. So that would actually allow me to conclude that the voltage drop along here is also 12 volts. So now let's take a look at what would happen if I had multiple resistors. Okay, so let's say my battery or my power source again has 12 volts. Then here, if I am the current, well, if we have a current, I won't be the current. If we have a current going through this circuit, it hits a resistor. All right, so it hits a slide, but that slide doesn't go all the way to the bottom. It might actually go to another slide. Okay? So what's happened here is and let's say these slides are equal in length. Okay, so if I'm going up 12 volts and I have two slides that are equal in length, then each of these slides must have a drop of 6 volts. And so that can tell me that each of my resistors has a voltage drop of 6 volts. Okay. So now we have looked at voltage in these two different scenarios. I'm going to give you one more scenario in which we have another 12-volt power source. Whoops. Oh, my drawings. Another 12-volt power source. And I have two resistors again, but let's say they don't exactly have the same voltage drop. Let's say this one only has is only about 3 volts. Okay, so let's say I have a slide like that. So it's a 3-volt drop. Then I know that this other slide goes all the way to the bottom because it's a complete circuit, right? So if this only gives me a drop of 3 volts, then this slide must have a drop of about 9 volts. So that means my voltage across this resistor is 9 volts, okay? So when we have something that is in series, when we have circuits in series, the voltage from our power source must equal the total voltage drop of each of our resistors. Okay? So another way to say that is our total voltage equals our voltage across all of the resistors. And that could be an infinite number of resistors. It doesn't mean that there is just one or the same voltage across each of the resistors. We've noticed 3 different scenarios in which there is a different voltage across all of those resistors. So now I want to take a look at some of the other variables. Let's take a look at current. Okay, so let's say I have a current of 4 amperes. And I have, so my current that is released from this battery is 4 amperes. All right, 4 amps. All right, so let's say that's 4 little stick figures going up these slides. My 4 little dudes going up the sides. So they go up the sides. Coming down this during this resistor, we will have all 4 of them going down, because one's not just going to stop here, because then all the other 3 are going to go down. They're going to try to come up, and they're going to push the other guy. So all 4 are going to come down. So what we actually notice in circuits that are in series is that all parts of the circuit will have the same current. So you have 4 going up, you have 4 coming down. And that's kind of the same in all of these scenarios. If you have 4 little guys going here, because there's only one path for them to all go through, they're all going to go down each of those slides. All right? So all 4 of these guys here means all 4 of these guys are coming down here and here. And because I am saying guys, and I'm not giving their hair, but they're all gender neutral, so don't worry. All my superheroes. Ooh, there we go. I put a cape. Okay, so 4 amps are going through the entire circuit here. So that means there's 4 amps on this side of the circuit. So no matter where we measure the amps, they are actually all the same in circuit. And you might actually even see what's called an ammeter. An ammeter is a tool that measures the current in a certain location along a circuit. And everywhere along a circuit that is set up in series will have the same amount of current. So it doesn't matter if you measure it here, or sorry, that should be an A. It doesn't matter if you measure it here. It doesn't matter if you measure it here. Because I have 4 amps in all of those different, in all of those circuits, and there's only one path, at any point there are going to be 4 amperes. 4 little guys going through in that circuit. So the current does not change anywhere along a circuit that is set up in series. So we can actually come to this conclusion. Okay, so the voltage is equal to all of the voltages combined. The current is equal at every point along the circuit. And now let's take a look at resistance. What's going on with resistance?